Hi. Today we'll talk about OP-based blocks. Okay. So let's quickly go over some OP-based topology. So then we can apply what we have learned last week on feedback. Okay. So again, OP is basically a high gain amplifier. Okay, and it has usually have three terminals, or it can have four terminals as well. So there is a plus terminal, negative terminal, and the output. Okay, the definition of plus and the minus is like this. So if input goes plus terminal goes high, and if output also goes high, then that's plus terminal. If the input of negative terminal goes high, then the output should go low. Okay, so that defines what is the relationship between plus terminal and output and negative terminal and output. Okay, so so this is very important because so this may cause your negative feedback become positive, so it may oscillate if you don't hook up the right terminal. Okay, so let's see. If we want a negative feedback, right? So we should have something plus minus, right? Okay. Then we have a feedback network, right? So we have a block as a feedback. Okay. So this is the original signal flow, and your feedback signal adding to the negative terminal, right? So a example of the feedback network is a divider, right? Resistor divider. So something like this. Okay. So this is what we have learned last week, right? And the feedback network has a gain of beta, which will be R1 and R2 will be feedback factor of R1 plus R2, right? So this actually, as we showed last week, this will actually desensitize the gain of OP, and your closed loop gain will actually be A plus 1 A beta, and because the open loop gain A is so big, so it becomes 1 over beta, right? So it becomes 1 plus R1 divided by R2. Okay, this is what we learned last week. Okay, what if I slightly change here? This is minus and this is plus. Okay, or this still work? Okay, so let's see if this will work. Okay. So suppose when input goes high, right? Input goes high. So then your output will go low, right? Your output will go low. Now, so because this is a purely resistor divider, right? Doesn't, so this will go low as well, right? So what you see is your input will be far apart. Okay, so negative terminal goes very high and positive terminal goes very low. So this will be further going down. The output will be further going down. So you're stuck so eventually this will go to the clamped by the supply rail and be very negative. Okay, so this will not work. This will stop. The output will be very low. Okay, so let's kind of review what we have before. So this is plus and this is minus. Okay, so if input goes high, so the output also goes high, and when after feedback, the negative side also goes high. Okay, and these two tracks each other and subtract. So your input is still close to the input. I mean the plus side minus negative side is close to 0. So this will be stable. Okay, and you see your output will follow input. Okay, so this is what we have learned using the feedback. Okay, so here we can have multiple ways of analyzing this circuit. Okay, the other way is using the because using the property of op-amp. Okay, the properties of op-amps. So first one is called virtual open. Virtual open. Okay, it's open. It's virtually open. Okay, so that this means has no input current. No input current. So that means so let me redraw the block here. Okay, so 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 this will be something. This is exactly what we did shown before, right? So this is R1 and R2, and just to a little bit redraw a little bit to make the circuit more to draw it a little bit bigger. Okay, so so suppose there's a current flow here, okay, and the current flow here, okay. So suppose if you have the voltage here, then current will flow down, right? So if it's bigger than 0. So and this is output has current flow to here, okay. Well, this current flow back to the negative terminal, so there's no okay, there's no current going there. So all the current flows through R1, which is I1, or equals to the current flows through R2, which is I2. So that means I1 or equal to I2. Okay, so that's the first property of op-amp. Okay, no input current. So it's virtual open. Second property is virtual short. Okay, for virtual short, that means we input at plus terminal is equal to the input at negative terminal. Okay, so it's like a short. But when we have short, the voltage is the same, right, between the wires, between the two ends of the wires. So virtual short means because the gain is so large, so it's always for your output to be within the supply rail, your input is very input with positive input minus negative input is very small. So for example, if the gain is 1 milli, right? So and your output is like within 2.5 volt. So your input has to be for your output to not to saturate. Okay, let's say like 2 volt or something, not hitting the rail. So if the output is 2 volt, so the input difference will have to be 2 volt divided by the loop gain, right? So the open loop gain will be 2 volt divided by 1 milli. So that's tiny, right? So basically you can think of because of the high gain of op-amp, this is due to the high gain of op-amp. Again of op-amp, then your the two input side is almost equals. Okay, so in that case, okay, if this is input, so this because of virtual short, so this voltage has to be the input also, right? So so then we know I2 will be V in divided by R2, right? Okay, because one side is V in, other side is ground, right? So and also we know how to define I1, right? Basically it's the voltage drop over R1, right? And this side is V out, and this side is V in, right? So we get this equation, right? So basically, if we reorganize, we get R2 of 1 plus R1 of 1 of V in, or equal to R1 of V out. Okay. So if we multiply every side by by R1, so that will be 1 plus R1 by R2 of V in. Okay. So that's the same as we get before, right? So the gain is roughly 1 plus R1 divided by R2. Okay. is the same as what we get using the feedback theory, right? So this is how we get using the op-amp properties, using the virtual short and virtual open. Okay, so so we call this non-inverting structure. Okay, so the input and output there's no negative gain, it's positive gain. So it has some good benefit. First is it provides positive gain. Okay, so in a lot of cases we need positive gain, right? Sometimes you may need a negative gain, but in a lot of cases you need positive gain. So if you can only do negative gain, you have to cascade 2 stages to get a positive gain, right? So if the stage itself can provide positive gain, that's very good. Second one, it has no input current from no input current. Okay, that means your is a high impedance input. Okay, so that means there is zero current drawing from the input side. Okay, this is very good, especially when your input is a very weak signal. So sometimes it doesn't provide much current. And if your op-amp is hooked up to the signal source, then if you need a large current, it doesn't work, right? It will destroy all the circuits you're trying to measure. So, but this one is a very good one. It doesn't need any current input, so it can measure the very weak signal. Okay. So this is due to property because we are hooking up to the op-amp input. So for op-amp, there is no input current. Okay. So let's study another one, which is the inverting style. So there's an inverting style or inverting structure. Okay. So for inverting style, that means your input is now hooked up to your negative side. Okay. And this side goes to ground. Okay. This ground is AC ground, means it's a fixed voltage. Okay. So what you do is you have R1 here and R2 here. Okay, this is the out and this is the in. Okay, so this is inverting because your input is no longer hooked up to the plus terminal, hooked up to the negative terminal. And as we shown here later, it provides negative gain. Okay, so let's see. Because of the virtual open, so the current flowing here has to flow this way. Okay, there's no current going inside the negative terminal. Okay, so that means I1 is equal to I2, right? I1 equal to I2. Okay, so because of virtual short, right? So we know this is 0 and this has to be AC0, right? If this is AC0, this has to be AC0. So then the I1 can be derived as V1 minus 0, right? And this side will equal to the current voltage drop across R2, and left side is 0, right side is the out, right? So then we have an equation, right? So we have V out over V in will equal to okay. So basically V out divided by V in, which is the transfer function, the edge transfer function, it will be minus R2 divided by R1. Okay, so this one you see, so the property of this one is you provide negative gain, right? Okay, this is also sometimes very useful because if you only have positive gain, there's no way for you can get negative gain, right? So you have to have negative gain. But if you only have negative gain, you can always cascade negative gain to get positive gain, right? So providing negative gain is, sometimes is essential. Okay, so as we shown later, so so it can providing provider providing also can also provide summing function. So instead of a gain stage, it can be a summer in either. Okay, see how that works. So basically, again, let me redraw this a little bit. So again, this is ground. So what you do is you provide another branch. So this is, let's say, V in 1 and V in 2. Okay. Let's call this R3 now. So this will be I1, this is I2, and this is I3. Okay. So so what you have now here is right now, then you have the current because of the virtual open, right? I1 plus I2 equals to I3. Okay, so your output then will be a summary of your input two voltages, right? Because I1 is V1 of V in 1 plus R2 of V in 2, and this is negative of R3 of V out. Okay, so V out will be negative R3 over R1 of V in 1 plus negative R3 over R2 of V in 2. Okay, so this is providing a summing function, right? So that's very useful as well. Okay, so can we provide this summing function using the non-inverting one? The answer is no, right? Okay, so let's go back. Let's quickly go back to the positive structure. Okay, if we go back to the non-inverting structure, okay, that will be plus negative, right? So what if you look up a something like this, and this is V in 1, and this is V in 2, okay, and this is R1 and R2. So this is V out. Okay, so what this will do? What's the output versus input? So what this will do is we try to find out the node x, Vx and Vy, right? So then we know Vx equal to Vy, right? So because of virtual short. So and what's the value of Vx then? Okay, because there is no current. So if there's no current coming there, so if there's a current, so then current has to flow from V in 1 to V in 2, or vice versa. So then Vx is very simple, right? Vx is this is R1 and R2, right? So basically R1 of V in 1 minus Vx will equal to R2 of Vx minus V in 2, right? So Vx will then be R2 of plus R1 of Vx will be equal to R1 of V in 1 plus R2 of V in 2. Okay, so Vx will then be R1 plus R2. Okay, we multiply every side by R1 and times R2. So this will be R2 V in 1 plus R1 V in 2. Okay, so that's very straightforward, right? So basically, we multiply every side by R1 times R2. So this one multiply R1 times R2 will be R1 plus R2 Vx, right? This will be R2 of V in 1, R1 of V in 2. Then we divide by everything by R1 plus R2. And that's Vx. So it will be Vy. Okay? And we know from before, Vy and Vout is Vout will be equal to 1 plus R2 over R1 of Vy, right? So then this is one equation, and this is another equation, and this is the second equation. So Vout will equal to 1 plus R2 divided by R1 of Vy, and which is Vx. So R1 plus R2. R2 V in 1 plus R1 V in 2. So right. So to summarize, then so the Vout will equal to R1 of R1 plus R2 multiplied by R1 plus R2 of R2 V in 1 plus R1 V in 2. Okay, so this cancels, so it will be R2 divided by R1 V in 1 plus V in 2. Oh, sorry. So this is my derivation is a little bit confusing. So let's rename it. So this is okay. Let's take this as R4 and R3. So this is instead of R2 or R1, it will be R4 over R3. So this is R4 over R3. Okay. So if that's the case, then you cannot cancel, right? So again, this is a special case. In the general case, if it's not only two variables, you have three different value of R's. So that will be 1 plus R4 divided by R3 multiplied by R1 plus R2. So R2 V in 1 plus R1 V in 2. Okay. So you basically providing some gain and a combination of input and output. Okay. It's also providing a summing function. So but the but the formula is quite different compared to the inverting case, right? Okay. So let's do one more exercise. Let's get really complicated. So what if we have both? So R1, R2, R3, R4, R5 minus plus. So for a case like this, right? So so if this is V in 1 and V in 2, so So what you can see, okay, again, so here will be no longer AC ground, right? And it has something to do with with your something to do with your gain, right? With your output. So this is Vx, and this will be Vx also, right? So and we know Vx and Vout has some relationship, right? So Vout equal to 1 plus R4 divided by R3 of Vx, right? And then for the input, then what you have, okay, for input, what do you have? Input is, again, you have this current equal to this current, right? So that will be V in 2, no, sorry, this V in 1 minus Vx of R1 plus R2 of V in 2 minus Vx will equal to R3 of Vx minus Vout, right? So again, so then you can organize a bit. So will be R1 of V in 1 plus R2 of V in 2 equal to minus R3 of V out plus R1 of V in 1 R1 of Vx plus R2 of Vx, right? So then you plug in this equation. So then you get the relationship of, so if you multiply everything by R1 plus R2, this is R2 being 1 plus R1 being 2 will equal to minus R3 of R1 R2 plus multiplied by 1 plus R3 of R4 dx, right? Plus R1 of dx plus R2. Oh, sorry. We multiply everything by R1 plus R2, so this will be plus R2 plus R1 dx. So if you get then you get an equation of dx equal to something, right? So dx will equal to R1 plus R2 minus R3 of R1 R2 1 plus R3 R4 divided by R3, and this is R2 being 1 plus R1 being 2, right? And then you hook up Vout will be this much. Multiply again 1 plus R4 divided by R3. Okay? So that's another example of how we can manipulate through the virtual short and virtual open equations. Okay? As the last one, let's see let's see a example called instrumentation amplifier, and it's very useful and used widely in everyday life. So what that has is R1, R2 to R1. Okay, so and then R3 and R4. So it's R3 and R4, and this one goes to ground. This guy goes to output, and this one hook up here. This one hook up here. Minus plus. Okay. So this is R2. Okay. So you have V in 1 here and V in 2 here. Okay, let's call this Vx, Va, and Vb. Vx and Vy. Okay? So, okay, let's do stage by stage, right? Virtually, you can think of this as a stage here on the left, and then another stage on the right, right? For stage on the left, right? So, if here is V in 1, that means this one also V in 1, right? So this will be V in 1 as well, and this will be V in 2 as well, right? So then you have a current flow, and this current flow has to equal to this current flow and this current flow, right? So basically, 2R1 of V in 1 minus V in 2 should equals the whole resistance, right? VA minus VB of R2 plus 2R1 plus R2, right? So we have a relationship between VA minus VB of this one will be simply be R1 of R1 plus R2 of V in 1 minus V in 2, right? So this is again, but basically differential example of the non-inverting cell, right? So this is very similar to what we have seen before. Okay. Now we have the gain stage of this one, so we can figure out what's VA and VB relationship with V input, V in 1 and V in 2, right? So then we need to find out what V out in terms of VA and VB, right? So so if this is VB and you have current flowing here, this is let's say I3. So I3 will be R3 plus R4, the whole thing, right? Which is dropped by VB, and also will equal to Vy dropped on R4, right? So we have established a relationship. Okay, this equation holds because there's no current going this way. There's no current going this way. Okay, so then we know Vy will be 1 plus R3 divided by R4 of VB. Right? So if we know this is Vy, so then Vx will equal to this one again, right? Because of the virtual short property of op-amp. Okay. So again, this one also have a relation, right? So let's call this I4, and there's no current going down here, right? So so for that one, so what that says is basically VA minus Vx over R3 will be 4 of Vx minus Vout. Right. So if we reorganize a bit, so that will be VA over R3 plus so we need to move all the Vx to one side, right? Plus so minus R3 of 1 plus R4 of 1 of Vx equal to minus R4 Vout. So, and then we plug in this Vx, okay? So that means VA over R3 minus R3 R4 of R4 plus R3 of Vx, right? Multiplied by R4 of R3 plus hold on, let me double check. EB. Oh, sorry, I made a mistake. Here is not Vy is R3 plus R4 of R4 dV. Okay, I just flipped it. So, so Vx is this much. So then this one is R4 of R3 plus R4 of Vb, or equal to minus R4 V out. Okay, so this cancel. Okay, so then we get R3 of Va minus Vb will be equal to minus R4 of V out. Okay, again, that means right? Okay, so it's like an inverting style. Okay, V out is minus R4 divided by R3, R4 divided by R3 of Va minus Vb. Okay, it's like an inverting style. Okay, so and we know Va minus Vb is actually equal to 1 plus 2 divided by R1 of V1 minus V2, right? So then we get the whole thing, we plug in the whole thing, so it will be minus R4 over R3 of 1 plus R2 divided by R1 of V1 minus V2. Okay? So that's something called instrumentation amplifier, and it's the gain is equal to the gain of K1 of V1 minus K of V2, right? So it is equal to K times of V in 1 minus V in 2. And K will equal to minus R3, R4 divided by R3 of 1 plus R2 divided by R1. Okay? So this also has the benefit of no input current, doesn't do any input current. And also has the function of converting differential signal to a single-net output. Right? You have V in 1 and V in 2. You have two input. This could be differential, and then you convert to a single-net output. Okay? So this is widely used in in high-end instrumentation devices such as telescope, like industry control, etc., etc. Right? Okay, so that's so much for op-amp related op-amp and resistor related circuits. So you should now be very familiar with the two properties of op-amp, which is virtual short and virtual open. And you can, using that two properties to analysis a number of circuits. Okay, that's so much for this one.